Okay. So today we're going to talk about another application topic, exponential growth and decay. They come in the form of word problems. Just want to talk about them a little bit. Growth and decay before we jump into them. As far as word problems go, these won't be or shouldn't be too complicated. We're going to be doing much more involved word problems, but it's an important topic that you should know. It will apply to not only economics like marginal functions, but it applies to a much wider range of problems, actually. So let's talk about what these guys are. Quantity is said to change, meaning grow, get larger, get smaller, exponentially. If it changes by a fixed percentage amount, of its current size, aka it changes, or i.e. maybe, it changes at a rate proportional to its current size. So anything that does that, we say it grows exponentially, or it decreases or decays exponentially. Growth just means get bigger, decay gets smaller. Okay? But if it grows by a fixed percentage amount, so it's not always growing by the same amount all the time, it's growing by the same percentage. So it might grow by 10% every week or something like that. So of course, from week to week, the amount is growing by is changing because 10% of something bigger gives you something bigger. So things that grow like that, we say they grow exponentially. Now, why do we call it that? Is because if P of t represents the amount of an exponentially growing quantity, then what you can say here based on this definition is the growth rate, or the rate of growth here, which we can talk about P prime, how fast P is changing, is proportional to the current value of P. So R here is a constant, and P is referring to the amount of the quantity that you have. Okay? Now we can solve this. Now we don't know the calculus, it's not complicated calculus needed to solve this, but we just haven't covered the topic yet. We can solve this. This guy here is called a differential equation. It's so called because there's a derivative in it. Okay. Now solving a differential equation means to rewrite the relationship without the derivative. So we can solve this to get this expression. P equals P naught e to the RT. And maybe after later in the semester, after we do integration, I can probably even show you how we can go from this to that. But this would be the main formula here. Now, in this formula, you need to know what the pieces are. So P of t, which I wrote as P here, is the current amount at time t. P naught is the initial amount. So however much you started with, t is of course time, this is going to be very important here. The phrasing is going to be important because the way that R is referred to and the way that P prime is referred to is somewhat similar, so you have to be very careful here. R is referred to as the relative growth rate. It's also referred to as the growth constant. And what it is, it is the percentage amount that we mentioned before as a decimal. So if I mention, oh, we have an exponentially growing quantity, it's growing by 10% per year, what that means is you'd set your little r equals 0.1. Right? So that's the actual percentage amount. But this is how it's called, the relative growth rate. Now, when you talk about just growth rate, not relative growth rate, that's your P prime. So P prime, this guy is just called the growth rate. So it's the overall growth. It's called the growth rate, it's called the rate of growth. Rate of change, that kind of thing. So it's how fast the overall population is growing. So that's the rate of change of P, right? So growth constant and relative growth rate is different from just plain old growth rate. It's a little bit confusing, but just make sure you know the distinction between these two phrases. And yeah, so these are two of the main equations that we want to know. The differential equation comes from the definition, but you can actually rewrite it without derivatives, and that's what it would look like, the PERT formula. Now, when you have something that's growing, there are very common things that we would like to ask. One thing that we would like to know about, which is often the case, is the time to double. So, if I know something is growing exponentially, a very common question is, how long would it take to double in size? So this I will refer to as T sub D, the time, but it's to double. Now what does that mean? Well, it means if you start out with P naught, e to the r, after some time, specifically the time to double, you will end up with double what you started with. So we can actually solve for this, divide both sides by P naught, you get 2 equals e to the RTD. You can ln both sides because that will kill the e, and you can solve for your time to double. Your time to double is going to be ln 2 over r. That's also an important equation. It gives you the doubling time equation. Of course, this also means that you can find r if you know the doubling time. So sometimes you'll be given information to find r directly, but sometimes we might just tell you, oh, we were watching this exponentially growing quantity, we noticed that after 2 days it doubled. You can actually figure out what percentage it's growing by using this equation. So this is also true. You can solve for one or the other. But this is the doubling time equation. Now, exponential decay. So these equations that I just told you about deal with exponential growth. Decay just means that there's a decrease. A decrease means a negative slope. So the main differential equation for decay would look like P prime equals minus RP. And we can solve this one to get P equals P naught e to the minus RT. So when you look at this with a positive power, positive R, this is growth. And with a negative R, this is decay. Now, otherwise the interpretations are the same. Your P naught represents the same thing. The letters themselves are all the same thing. The difference is when the power is negative, it looks like e to a negative power, so this thing is going to go down like that. When it's positive, it's like e to a positive power. It's going to shoot up like that. A very important thing with exponentially decaying quantities, something that's commonly mentioned, commonly sought after, commonly tracked, is what's called the half-life. So, those of you who are doing science classes, you'll have no doubt have heard of this word before. So this is half-life. We'll call it T sub h, and this is time to add half of what you started with. So you have a quantity that's actually getting smaller. It's decreasing over time, decreasing exponentially. You might ask, how long before I have half of what we started with? That time is called a half-life. Now, of course, you can solve for this in the same way. If I started with P naught, e to the minus r, when the half-life has passed, I would have half of what I started with. And so now I can actually solve for what that guy would look like. Divide both sides by P naught, get 1/2 e to the minus r t h. You can ln both sides. And so you can solve for the half-life. The half-life is going to be ln of minus ln of a half over r. Now, one thing you can notice about ln of a half. Ln of a half, you can think of that as ln of 2 to the minus 1, which you can just bring the minus down in front, and that gives you minus ln 2. Or you can think of ln of a half as ln of 1 minus ln of 2. That's using a different log rule. Log of 1 is 0, so this is, again, minus ln 2. In other words, ln of a half is negative ln 2. So if I have negative ln of a half, I can think of this as positive ln 2. And so my half-life here is ln 2 over r. So if you have an exponentially decaying thing, and you know the half-life in a second, you can actually find r, or find the half-life, or find either one by using this equation. Yeah, you had a question?
Yeah. Why does it like work out that the equation is the same for doubling and like half-life?
Yeah, the equation is going to be the same, but the difference is in the growth you're going to have a positive here, and in the decay you're going to have a negative here. So when you actually plug it in, it's going to, this one is going to be halved while that one's going to be doubled, because this one has a positive power versus a negative power. So it'll look the same, but the difference comes in the fact that you put in this negative here. That's going to make the changes. You can also notice something else. So for time to double, I asked how long before I get 2 times what I had. Notice that I could have asked time to triple, time to quadruple. And you would have just put the right number here. So the time to triple would be ln 3 over r. The time to quadruple will be ln 4 over r, etc. Same thing here. If I ask, how long will it take to have a quarter of what I started with? ln 4 over r, etc. You can do that. But halve and doubling is very common to ask about. They're both going to give you ln 2 over r. In the growth formula, this will actually make things bigger because there's a positive power. If I plug in the same ln 2 over r in the decay formula, it would make it smaller because of the negative power. Yeah?
Why did the negative cancel out of the numerator for ln 2?
Oh, because ln of a half is minus ln 2. I just showed it here.
Yeah, but like why isn't it the negative in front of the ln 2 in the final equation?
Because it canceled. Because I have negative, ln of a half is negative ln 2. So negative cancels negative.
Oh, okay.
So the half-life and the doubling time equation, they're going to look very similar, but they will have very different effects because the formula you're plugging it in is going to have that effect built in. So those are the main equations. Just wanted to kind of show you where they came from. Oh, that's the equation. But as you can see, I collected those in two boxes. So you have a box here for your growth formulas, you have a box here for your decay formulas. They're both exponential changes, but that one gets bigger, that one gets smaller. And the difference is you put a minus r instead of a positive r. But other than that, things will work out very similarly. That's what the variables mean. Another application that you'll see is the phrase compounded continuously. So sometimes you have something like that. Usually that phrase is used in a financial context. Compounded continuously literally means exponential growth. It's a synonym for exponential growth. So if you see it compounded continuously in some context, it means that it's governed by this equation. So these are the formulas for growth, those are the formulas for decay. Depending on the situation, you'll know which set of formulas are relevant to the problem that you're looking at. Other than that, what you want to know about this topic is just how to recognize that you're actually looking at this topic, because on like a test or a quiz or something like that, I'm not going to tell you, oh, this is the topic that you should be thinking about. You'll have a bunch of word problems from all over the place, and you need to identify, okay, which kind of word problem am I looking at now? And the phrases you want to look for are phrases like the word exponential, proportional to its current size, radioactive, half-life, doubling time. All these key phrases that I was mentioning here will kind of indicate to you that it's an exponential growth and decay problem. That being said, we're going to go through a couple of examples here just to get used to using these equations. So let's actually do that. Let's actually see how to actually put this all together to solve a problem. So we're going to start off with problem 1. And I'm going to let you guys do problem 2. And we'll see if we have any questions from there on what's going on. One. Okay, so first let's read this. So P of T is the current size of a population of bacteria. At 10 a.m. there are 50 bacteria, and at 3 p.m. there are 350. So it grew 300 strong in that time period. Assume the rate of growth of the population is proportional to its current size. That phrase tells you that you should be thinking exponential growth. So again, it says growth proportional to current size. That phrase tells you you're talking about exponential growth. That phrase tells you all the equations in this first box are now relevant to the problem that you're looking at. Okay, so A, find the relative growth rate of the population. So they're asking us for a relative growth rate. What is that relative growth rate? Who are they asking for? What are they asking for? Yeah? They're asking for R, little r. Okay, how do we find little r? So you know you're going to have to use one of the equations over here to try to find little r. So you're going to use the equation where you know enough data to solve for the r. Which one's that going to be? Yeah?
P equals P naught e to the RT.
Okay. Fill in what we know here.
P is equal to 350. And then 50 is P naught. And then e to the R times 5.
Alright, so here we're measuring time, measured in hours. So you have all this information here. You know that if we started out with 50, when time hits 5, we have 350. Yeah?
Is there like when we're calculating time, does it always have to be in like hours or like days?
No, it will depend on the
Or
situation.
every problem?
Yeah, every problem would have its own thing. Yeah, so there's no standard time value, just go by the wording of the problem. Here you're actually mentioned time on a clock, so hours seemed like very natural to use. But as you might see in problem by 2, it specifically mentioned years, so the problem is,
Just keep
yeah, just keep the units based on the problem itself. So, how would you solve for r here? Divide by 50, line both sides, I'll kill the e over here, and then you would divide by 5. So, that is the answer to the first one. That's your relative growth rate, ln of 7 over 5. So in B, ask for a formula for P of t. We already know the general formula for P of t. P of t is equal to P naught e to the RT. Now, how you want to look at this is, of course, your P is like the output variable, that's like your Y. Your T is like the input variable, that's like your X. So in the same way that you'd have like Y equals f of X, you are going to leave, when they ask you for a general formula, you want the P and the T to stay there. What you do want is to make sure you find everyone else. So you need to find the P naught, you need to plug that in, you need to find the R, you need to plug that in, and you leave everyone else alone. And so that actually, we know everyone else already, so the P is equal to 50, that was our P naught, E, and we just found the R, ln of 7 over 5 times T. What's that? C. What is the size at 4 p.m.? So how many bacteria would we have at 4 p.m.? Yeah, Mark?
You could use that equation, but plug in T, or plug in 6 for T.
Here, T equals 6 hours here. Alright, so it starts all off at 10 a.m. We're measuring time in hours. So, yeah, this is just going to be asking for a P of 6, which is 50 e to the ln of 7 over 5 times 6. And whatever that is, that's the answer. If you can't use a calculator, you just leave your answer like that. D. Rate of growth at 4 p.m. Yeah?
I have a question for C. Would it be wrong to put the P of 0 at like 350 and then say an hour for T? Like instead of like the 10 a.m. is 50 bacteria, like you use 350?
It wouldn't be wrong. I wouldn't recommend it though, but it's not wrong to say that. So you could have changed P naught equals 350. And you know it's 350 at 3 p.m. So yeah, if you had done P of 1 starting from 350, and then you have ln of 7 over 5, and you just plug in 1, that's actually going to give you the same answer. But I would say once you have the P naught from the beginning, I would leave the same P naught and just measure everything from the original. I think you start changing too many things. You might run into issues. It's not wrong though. That answer is actually correct. Okay, so rate of growth. What's that? Yeah? Right, that's the P prime. And we know from our formulas that P prime is equal to R times P. So we want the rate of growth after 6 hours. R is ln of 7 over 5. And I want the amount at 6 hours. So this is ln of 7 over 5 times 50 e to the ln of 7. Times 6. Whatever answer was right. whatever that answer was, you're just gonna plug it in here, plug in your R. That's your rate of growth. That's how fast it's growing after 6 hours. At that point, that's how many new bacteria are developing per hour. When will the population be 1,500? So we started off with 50. How long before we get to 1,500? Yeah.
So use your P equals P naught RT equation, and then you have 1,500 equals 50 e to the power of ln 7 over 5, and then you solve for t.
Right, so when means you want to find time. So plug in all this, the population, the current population is 1,500. You started with 50. You want to find how long that takes. When did that happen? So you can divide both sides by 50. That's going to be 30 over here. ln both sides. We can solve for t. T would be 5 ln 30 over ln 7. And that's whatever in hours. Any other questions? Alright, try problem 2. Give you guys 5 minutes to do problem 2. let's read this one. I've given enough time. So the half-life of a radioactive substance is 30 years. Again, things like half-life, radioactive, phrases like that imply to you that you're talking about exponential decay. Okay. So we know the half-life is 30 years. Supposed to start with a 200 milligram sample of the substance. P of t is the mass remaining after t years, so time is measured in years in this problem. A, find the differential equation satisfied by P of t. So A. What's the differential equation?
Isn't it just P prime equals R2?
Says P prime equals minus RP, right? Because it's
Minus
decay. So you need that negative there. Now, of course, your R is what you want to find. How do you find that R?
Use the half exponent.
So now we know that half-life is equal to ln 2 over R. This means 30 is equal to ln 2 over R. This means that R is equal to ln 2 over 30. And so P prime equals minus ln 2 over 30P. That is your differential equation. B. Find a formula for P of t. Okay, so want the general formula for P of t. That one's that's about, we know that P of t equals P naught e to the minus r t. What's our P naught here? So plug in 200. E to the minus, we just found r, ln 2 over 30 times t. That's our equation. How much will remain after 75 years? How do we find that? Yep,
You're just plugging 75 in for T.
just plug in 75 in for t. So this is just, this is P of 75, which is going to be 200 e to the minus ln 2 over 30, putting 75 here. Now, that's going to be something that you won't have to calculate, you just write that down, that's it. After how many years will the mass be 1? So, how long before we get to 1 milligram? How do we do that? Yeah, Mark?
So put in 1 for P of t
1 for P.
equals 200 P to the negative ln 2 over 30.
You want to solve for T, because for how many years you want to solve for time? How did you solve that?
You ln both sides, get ln 1 over 200.
Oh, so you first divide both sides by 200?
Yeah.
Then you ln both sides. So,
200, yeah,
take 1 over 200 equals e to the minus ln 2 over 30t. You ln both sides, ln of 1 over 200 equals minus ln 2 over 30t. Then,
you get 30
so your t is going to be, multiply both sides by 30. and then divide by the ln2. Now, seeing the minus here might freak some of you out about negative time, but it's not negative because the truth is your ln of 1 over 200 is actually a negative number. So just like we had like last time, realize that this guy here is actually, say, ln of 200 to the minus 1, so you can bring that minus 1 down. It's minus ln of 200, and so this is actually positive 30 times ln of 200 over ln of 2. And that's clearly positive, so that actually makes sense. And what is the rate of growth at the time there is 1 milligram remaining? Yeah?
So it would be 1 equals 200 e to the r, so we plug in that into.
Well, what is rate of growth referring to here?
What did you say?
Yeah, but what variable is that referring to?
Is it r?
P prime.
Referring to p prime. Right. So that one is understandably confusing. So that's why you have to really know the phraseology here. So you have to remember that when you talk about r, it's not just rate of growth or growth rate. They emphasize relative in that phrase. It's relative growth rate. Right? Or they might even call it the growth constant. Or they might call it the decay constant. Now, when you just mention growth rate in general, like just growth rate, plain old growth rate, or rate of growth, that's referring to your p prime. So here we want to find p prime, which we know is that. And now we know what r is. R is ln 2 over 30. And we want the rate of growth when 1 milligram remains. So you literally plug in p equals 1. So p prime is just equal to minus ln 2 over 30 when 1 milligram remains. That's that. So be careful of the phrasing there. Growth rate, you have 2 different variables that has the word growth rate in it. So you want to be careful that you're not mixing them up. The little r is the relative growth rate. That being said, we'll actually stop there. Try the third one for next week. Next week our quiz is going to cover everything up to here since the last test. Also, I finally remembered to actually post the solutions to the test. So here's what I would say. So you'll notice that on the test I wrote your grades. If you got any bonus points, your grade might look like, let's say 78 plus 5 or something like that. That means you got a 78 on the test and 5 points from the bonus. Now your total grade, I would actually add these, so your actual grade that I'm going to enter into the report would be an 83 in this case, but the grade in the circle indicates what you got without the bonus. Now what I would say is if this is less than 70, I would suggest you see me. We want to make sure we understand what went wrong, what was off about this time, and what we can do to improve for next time. Before doing that though, what I would say, I think it would be very beneficial for you to go over your test, try to actually redo what you got wrong just by yourself. Then you can check my solution, see if you got it correct. and then you can come see me, because that will actually give us some useful data. If you could do it now, but you couldn't do it on the test, that indicates something completely different than, even now I couldn't do it, you know? So by trying that, you'll know for sure, was it the test that was the issue, was it a timing issue, or was it I actually don't know how to do this problem, right? You do want to know that. So try to go through it on your own, check my solutions to see where you are, and then come see me, we'll talk about it, and talk about what you can do to do better next time. I will see you guys then. Have a good weekend.